I hope the presentation is visible and I am audible. So yesterday we started with the problem that is designing a non-deterministic PDA to see its strength. Okay. So the question that we had taken was the region A and region B are different, right? Which means it can be shown like this also: A power M, B power N, where M is not equal to N, and they cannot be 0 also. It has to be greater than 0. So in a nutshell, not equal to is very difficult to show. What they are saying is number of A's and number of B's should be different, right? The question says number of A's and number of B's should be different. But it's very difficult to emulate a negativity or negative symbol like not equal to. So what we can do is we can divide the same question into two portions like this. Okay. So not equal to means what? Either A's are more or B's are more. Correct? So if M is less than N, then B's are more, because you can see N is written for B. So if M is less than N, that means A's are less or B's are more. Similarly, if N is less than M, it means that A's are more. Right? So some of the examples for B's being more. Correct? Similarly, these are the examples for the alphabet A being more in number than B. Okay. So we designed this also yesterday. For example, the logic we implemented when we designed was, suppose if I see a C, because we know how to design for A power N, B power N, right? All A's should be pushed into the stack, and when B comes, you have to pop. Only thing is here they are not equal. Okay. So if you see A in the input, then we stay in the state A, 1. And we push all A's. Why this pushing and popping business is because after B you cannot have A. For example, this question also says that you have unequal number of A's and B's, but this is not the language we are designing, right? So because of that, we should make sure that once we get the first B, there should be no scope to get A. So whenever you get A, just stay in state 1. You can see here, get A. It doesn't matter what is there in the stack, right? It could be an empty stack or there could be anything else in the stack. Just push it, right? So for A's simple action, deterministic, right? It's deterministic. Why? Because we know that if we get A in the input, it doesn't matter what is there in the stack, we are going to push it. So it's a deterministic action. When I see the first B, and if the top of the stack is A, then pop it, correct? So that's what we see, and also make a state change from 1 to 2. So if you see B for the first time, pop A, consume B, and move to state 2, right? Once you are in state 2, if you get B as input, and if there is A in the stack, we are going to pop it. All right. Now the situation is that we might run out of places where we can apply this anymore. We have already come to B. Till here it was deterministic. There were no two paths. It's always fixed. Only this is what is going to happen. Once you come to state B, what happens? At some particular time, you might either run out of the input. When will you run out of the input? Suppose I have more A's than B's, right? Then I have put A's into stack, and for some B I have taken A out of the stack, and there is no more input, right? But there are some things in the stack. I might come to a situation like this. So this represents more A's case, correct? Or I might come across a situation where I may still have B's, but nothing is there in the stack. So when will this happen? So you pushed A into the stack. For a B, you pop this A, and you have input now, but there is nothing in the stack. All right. So we might come across these two situations, and we have to come across these two situations to accept the input, because unequal number of A's and B's means you have to come across those situations to accept the input. Okay. So let us see what to do now. Suppose if I see a B, then I should change state, isn't it? As I said, I'll be in state 2 until there are equal number of A's and B's. Now A's are over. So if you see a B, you will go to final state, right? That means more number of A's than B's. All right. Or else, even if B's are over and if you have something in the stack which is A, you should come to, you should change the state and come to an acceptance state. Because we divided the problem into two separate problems, so these are the two separate solutions. If it's a more A, you will come here, and if it's a more B, you will come here. So once you come here, then if you find any number of A's, you will remain it. Anyway, you are in the final state, and similarly with this. Now, what is the problem with this? Okay, this is non-deterministic, but does it have a problem? Yes, it has a problem, because you might have seen in all the problems that we designed till now that you could write something like this, right? It doesn't matter what is there in the stack, you're going to push, or if there is a particular input and particular thing in the stack, we are going to pop. And in PDA, there is no way for me to force the machine to take a direction when stack is empty, or the machine to take a path when there is no input. Okay. So you might say, but you have written it here. That's what I'm talking about. These are non-deterministic. I am not forcing the movement when stack is empty, because there is no way I can show stack is empty. Okay. I told you, the second field, when there is an epsilon, I said anything could be there, isn't it? Anything could be there in the stack. So same thing applies here also, isn't it? Anything could be there in the stack. So now I don't know, each time I get a B, no? I match two things, right? So B on A or B on anything. So what happens is I take multiple paths. Even the other thing is, I don't know how to represent when there is no input in PDA. We haven't used any, transitions to represent that. So you can see that's what I have written here. So in order to accept, we know now that we have to read at least one B which is not having a matching A, right? And we go to state 4. Or we have to pop A without matching B, means input is over but in stack something is there. So in which case we went to state 3. And as I said again, there is no way to specify a move which can be made if and only if stack is empty. In the previous case, we did 2 moves. So whenever you got a B, actually stack is empty means you should be going only to 4 and not just take 2 paths. Okay, you should not be there in 2 also and go to 4 also. But that's what we are doing. Okay, and unfortunately, there is no way that we have learned to specify that input is empty. Input is empty means what? Something is there in the stack, but there is nothing as a input. So because of these 2 reasons, because we do not know how to specify a PDA transition for these 2, what happens is when you are in state 2, mostly you will be taking multiple paths. Is there any problem in multiple paths? That is there in the definition of non-determinism, isn't it? Taking multiple paths. But if you remember, when we studied DFSM and NDFSM also, we preferred DFSM because it doesn't waste any effort. It is deterministic, only one action per a condition. But NDFSM is, you will be doing multiple actions per condition. So what we did was we learned an algorithm, easier to write NDFSM, so we'll design NDFSM, but we also learned an algorithm which will convert NDFSM to DFSM. Okay, because the advantages, because of the NDFSM is very strong, easy to design, and it can do multiple things. So NDFSM is very strong, but DFSM is very efficient. Any deterministic machine is more efficient than the non-deterministic machine. So now what is the solution? Here there is, in case of PDA, I told you that it's very important to remember for many NPDAs, that is non-deterministic PDAs, there may not be equivalent. For many, not for all, there may not be equivalent deterministic PDAs. Okay. Then what can we do? Because NDAPA is strong for design point of view, DPDA is good efficiency point of view, but as we are making an important point that I told you that NPDA means computational effort will be wasted, isn't it? First, why did I say first? Because whenever you take multiple paths, you remember, no, one of them will go to accepting stage. If I have designed it for, let us say, AABBB, right? Among the multiple paths it might take, many will die, but at least one path will be accepted. But we are talking about wasting traversing these paths. So what do I do? If I have a deterministic machine, then these things will never be there. There will be only one path, and that path will take you to acceptance. Correct? So as I said, now I cannot convert it into deterministic. So the next best solution is, right, to reduce non-determinism. So the solution we are going to see is, of course, non-determinism will be there, but we are going to reduce it. Okay, so reduce non-determinism. So in the question above, to reduce non-determinism, one thing I told you, there was no way to represent stack empty, correct? That is, you couldn't force to make a transition when stack is empty. And the second thing I told was, there was no way to represent when the input is not there, right? Input has ended. So there was no way to force a transition to be taken when the input has ended, and there was no way to force a transition to be made when the stack is empty. So the solution revolves around these two. Okay, that is, let us find a way to show stack is empty. Also find a way to show input is exhausted. Input has exhausted. Okay, so that's what we'll discuss now. I think I'll take only 10 minutes from here onwards, and you can relax after that. Okay, so let us take that. Before we move on, let me put this diagram for you to refer. Okay, this is what we designed till now. Okay, so the first solution I am going to take to show you to reduce non-determinism or to eliminate non-determinism. So check for an empty stack. Okay, first solution is write something to check for empty stack. So how do I check for empty stack? We will only use a bottom of stack marker. You remember now in data structure, I think in infix to postfix conversion program also, you had written that you pushed hash into the stack before anything else. So here also use bottom of stack marker. We can use any symbol, but we'll use hash. Okay. So that means before you do any of this, whatever I have shown in this diagram, okay, we'll introduce a state called as, let us say state 0. Okay, let's call a state called as 0. Just introducing it. And the first thing I will do in that state is, Doesn't matter what is my input or doesn't matter what is there currently I mean nothing will be there currently in the stack, but doesn't matter. This means it doesn't matter, no matter what is there, I'm going to push hash into the stack. So first steps makes sure that the first symbol in the stack is not A, but it is hash. This is the bottom of the stack content. So now how will this diagram change? So this was already deterministic, isn't it? So we are not going to make any change to that part. Okay. So whenever you see A, doesn't matter what is there, push A will remain as it is. Whenever you see B first time and if you have A in the stack, pop and change the state to 2. Similarly, whenever you see B and you have A in the stack, pop it. So this will not change. Now what path will change? The path that will change is this part. Why? Because this is the path which when you have B, A's are over in the stack and you still have B, isn't it? So to this solution that we are using, check for empty stack, will change only this part, not this. This is the second solution. Okay. So to do this now what I'll do is, you can see, as I said, the upper portion will not change, so it will remain as it is. Till here, okay. So next what happens is, if you have, as I said, condition that we are going to make changes to is, if you have a B and the stack has hash, okay. Let us say here, when B is there and in the stack A is there, you wrote epsilon, right? But if you have B still and hash is there in the stack, that means we have exhaust, we still have B's but stack is over. In which case now we are forcing that this should not be taken as one of the paths along with this. Now it has become deterministic. If you have B and if you have reached the end of the stack, right? If you have reached the end of the stack, go to state 4. Go to state 4. Okay. And once you go to state 4, if you get B, doesn't matter what you do. Because we popped the hash here. Epsilon means pop, no? We popped the hash here. We force the transition to go here only. I hope this is clear. In this case, if you had B, you would take this path also and this path also. But now what you are doing? You are forcing this. Why were you taking two paths? Here B on A and here B on anything. But anything is removed and forced as hash. So now if the stack is empty, you will not take this path. So you are converting it into deterministic mode to go to final stage. And once you are in final stage, we popped hash already. So it doesn't matter what is there in the stack. We'll just keep quiet. Anyway, you are in the final state. So no action. Just consume B's. Just consume B's. Okay. I hope this is clear. All right. Now let us say you had you came to this thing, even in this diagram. Okay. This means what? B's were exhausted and you had A, right? You had A in the stack. So you kept on popping the A. So when will you stop this action? When you reach the hash, correct? You stop the action when you have hash in the bottom of the stack. Let me repeat this once more, okay? I'll repeat it fast. So as I told earlier, B on A or B on anything option was there. So whenever you got B's, you make two transitions. You will remain in B2 also and you will also move to 4. But now what you are doing is you are forcing that when you have bottom of the mark, means there is no A in the stack, but we have a bottom of the marker, then you are forcing the transition to come to stage 4. Okay, this is one change. The second change is, let us say your input had exhausted and you had A in the stack. You had A in the stack. Earlier what happened was this was the only action. No? Whenever you have A, you just keep on popping it. Right? But since you are in the final state, it wouldn't matter. But you will go on. This has no end. So when will you stop it? So I'm adding an end. Let us say I have reached the bottom of the stock. I popped A's. Now I have reached the bottom of the stack. So that will stop it. Okay, this action will be stopped. So this is one solution, right? Checking for empty stack is one solution. Now let us take the other one, out of input problem, and find the solution. Okay. Let me put this again, diagram. Okay, let us put this again. Right. So as we did earlier, we had taken care of, as I said, this will be a solution we are finding for out of input problem. We are going to keep the previous solution also, that is stack problem, and then add this solution. Okay. So at stage 0, as you know, what we did was we just pushed hash into the stack without making changes to input or other things. And state 1 was as it is, deterministic. Moving from state 1 to state 2 also was a deterministic action. So I was not going to change anything, right? And we had made a change from state 2 to 4. That is, if you had B and stack, you had reached hash, we forced the transition to come to 4, correct? And in 4, we said it doesn't matter after that if you get B, and because nothing, it doesn't matter what is there in the stack, all B's should be just consumed. This is what we wrote, isn't it? And we also made one more change, that is, in state 3, we made a change for acceptance here. So we had one transition, that was this. Along with that, we added a hash here, correct? When you reach the bottom of the stack. So till here it was there. So there was nothing that was there for this. Now the solution we are finding is when the input is over. That means what? When the input is over means what? Something is there in the stack, isn't it? For example, A, if I have this, 2 A's, 4 A's will be pushed, and for these 2 B's, these 2 A's will be popped. So in stack, you still have 2 A's left, isn't it? But the input is over. The input is over. So for that, what we'll do is, we'll use what is called as a dollar. Okay. We'll use dollar as end of string marker. We'll use dollar as the end of string marker. That means till now, if you are building a PDA to accept a language L, now we are actually building a PDA to accept a language called as L dollar. Okay. So it's a special symbol we are using, just like hash. So what will I do now? Just observe this part. Okay. Here it was, I don't know what is the input. If you have A in stack, pop it, right? So what we'll do is, we'll force a transition from state 2 to 3. State 2 to 3 solution is 3 is more A's than B's, correct? So when will I force? See, there is no input, dollar. If I encounter a dollar, that means I had added dollar to this, right? A, B, let us say dollar. And I had removed this. So I have encountered a dollar. In which case I am saying I am forcing you to go to stage 3. Okay. What is there in the stack? In stack, A is there. So dollar is the input, A is the stack. If this is the condition, it means you have more A's than B's. So you go to state 3. Since I am forcing this, you won't be taking multiple paths. You won't be taking this also and this also. Earlier, both could be taken. Why? See here, B, top of the stack is A, pop it. Doesn't matter what is the input, top of the stack is A, pop it. So two actions were taken. But now I am saying, if you have B on A, you be looping. or if you have reached dollar on A, make a forced transition, right? So once I added that, there is a small addition that will happen here also, because once the B's run out, you stop the transition. Because in this case, you will keep on getting B's forever, right? But we'll stop it somewhere. Now, after the B's are over, we'll stop it somewhere. So this is the solution for for reducing the non-determinism. Okay. So I have come to the chat section. Can you tell me if everything is clear? Next class we'll start with the fresh topic, conversion from PDA to CFG, which we had.